Okay, today's presentation is hardware designing smart home applications, rapid prototyping, and embedded systems. I'm Tao from Iowa State University. And first of all, research in smart home technology are highly diverse and innovative. One of the challenges in this area is how you can turn into innovative idea into actual hardware. In this paper, we present two methods that can facilitate these transitions. First of all, there are some existing commercial products available for purchase, such as X10 and Fidgets, and they are kind of commercialized and have very fixed functionalities. In this case, in this presentation, we focus on methods of facilitating in creating new hardwares. These hardwares will be used in smart home applications. They should have a wide applicability and high fidelity, and also they can be formally documented. And on the pictures here, you can see one of them is kind of X10 security camera. Another one is from Fidgets. These are commercially available. First of all, we'll talk about embedded systems. These are referred to as dedicated electronics, which performs real-time tasks such as sensor control and communications. And by using dedicated designed electronics, we can take advantage of the latest electronic developments, and as a result, these hardware are specifically designed for smart home applications. And on the right, you can see there's a kind of circuit schematics and circuit board layouts. So if double E, then you should be familiar with this kind of drawings. And the next method is rapid prototyping. This generally refers to 3D printings and laser cuttings and engravings, also kind of a 3D printing too. And typically they will start with a computer model, as you can see in the first pictures, and then there will be this computer model can be used to check some of the potential problems such as manufacturability, clearance, and strength and usability. And for smart home application, they can be used. They can be very fast and cheap, as demonstrated later in the example. So to show what we're talking about, we have two examples. And first of all, for typical smart home applications, these prototypes are small in size and scales. They are not terribly large, nor they are very big in numbers. And we also, in this case, we prefer a fast development for kind of to facilitate creating and refining new hardwares. And in the following slides, I'm going to talk about two methods, two prototypes developed in Iowa State Universities. Okay. The first one is called Life Companion. It's conceived as the physical well-being monitoring device, as you can see on the right pictures, for senior citizens. Basically, it's a wearable device that records various information such as physical activity detected by accelerometers, GPS location, temperature, and photos. And it's intended for both indoor and outdoor activities. Additionally, it functions as a device to relieve symptoms of early Alzheimer's disease by playing back users' location and what the user has seen captured by the camera to the user. And it can also serve as a panic button, which kind of sends the wireless distress signal to nearby Bluetooth enabled devices. In case of an involuntary fall, the prototype also kind of detect free fall situation and sends out the stress signal automatically. Okay. So in designing this device, first of all, we avoid similar functionality found in kind of existing commercial products such as smartphone and Flip, Life Alert, Microsoft SenseScan. What we have done is to avoid similar designs and also kind of at the same time combining some of their functionalities. So on the right, you can see there's like Life Alert. Basically, it's a free fall button, and alert button you can see that is worn by these elderly citizens. And in the bottom, you can see there's the design for Microsoft SenseScan. And some other design requirements are the physical compactness and simplicity in operations. So first of all, the circuit board was specifically designed using Eagle from CADSoft, and the circuit board was And integrated ICs were selected to meet the design requirements such as small in size and weight, wireless communication, battery life, and etc. And the circuit board was manufactured by Advanced Circuits. And the circuit board was the parts were soldered to the circuit board by simple reflow soldering. And in this slide, I'm talking about some rapid prototyping. And in this case, the case was designed in SolidWorks and manufactured by LaserCut plate. As you can see from the first version and the second one, we have significant reduction in size. One of the reasons why we can do that is because we can have we had more integrated circuits and smaller parts. Next slide. And here are some of the data collected by the device. And you can see there's a GPS chat recorded in yellow in the first top left picture, and also you can see a specific location that is what the user has seen from their perspective at that specific time rendered out in Google Earth. And in the bottom you can see accelerometers. Okay, cost breakdown. The total cost for each version is about $100 in total, and manufacturing for PCB is like 33, parts $60, and laser cutting is about $10. And the turnaround time is about, PCB manufacturing is about 5 days, 3 to 4 hours for soldering, and 2 to 3 hours for firmware and host software development, depending on the experience. Okay. The next example is like SmartLamp. And in this case, I'll just talk about some of the great features. It's a multi-color LED array for different intensity and color settings, and it also has an infrared distance sensor to detect the distance to the illuminated object, and also have an orientation sensor that detects whether it's in reading mode or general lighting mode. Here are the schematics and the pictures of that SmartLamp. Okay, discussion. And in this presentation, we present two methods that can be used effectively to model and manufacture distinct hardwares. And this method presented in this paper is very suitable for applications and coming up with new ideas in smart home environment. And like other technologies, this is a multidisciplinary area, and also whenever engineering designs are possible, these have to be constrained by usabilities and user friendliness. Okay, that will be the end of my discussion.